Assalamu alaikum. Today we'll be going through our work on identifying and flagging hallucination in LLMs. Now, we already know what hallucinations are, and they present themselves in both general and complex tasks. However, there is no general way of identifying these hallucinations. What motivated our study was the particular evolution of user behavior and interaction with LLMs, with the study showing over reliance on these models, with people blindly accepting their outputs without verification. And more surprisingly, they're still affected and influenced by these model outputs even when they are rejected. Now, current detection methods are limited, costly, and impractical. For example, Google proposed fine tuning a classifier on top of their LLM to detect hallucinations, but this is most of the time incorrect, but also costly and inflexible. Lastly, is a common sense approach of just displaying your token probabilities to the user and leaving it to them to identify whether the answer is correct or not. However, users may misinterpret these confidence values and not understand how to analyze them. So, we aim to develop methods to detect and flag hallucinations with minimal computational overhead. And our goal was to provide practical, generalizable solutions for hallucination detection using vanilla models in a simple way by utilizing the information they provide themselves. Now, our research questions was, can we use just the top token probability to set a threshold to identify hallucinations? If not, can we just ask the LLM to self assess its output and identify hallucinations? And lastly, we instead of depending on a single token probability, we could take a distribution of the top k token probabilities and see if the patterns reveal any differences between hallucination cases and correct cases. Now, for our methodology with the data sets, we focused on MCQ data sets because it's easier to identify correct and incorrect responses and evaluate our models. We used mixture of general purpose MCQ models to test on general tasks, but also niche and nuanced topics to test specific cases. We also added positional variations to these models as a separate testing methodology because of the positional biases in LLMs. This allows us to simulate a case with more hallucination cases to test our methods. We tested these methods on GPT 3.5, Llama, and Gamma for exhaustive testing. We used both proprietary and open source models to cover greater ground. We weren't able to use GPT 4.0, Gemini, and Claude models because of cost restrictions and because some of these models don't provide log probability values. Now, looking at the first method of just using the top token probability and setting a threshold to detect hallucinations or not, we analyzed the LLM outputs on multiple data sets and compared log probability values between correct and incorrect answers. Now, for correct answers, we found that they have a higher log probability concentration near the threshold that we identify. And we tested this threshold effectiveness across models and data sets. Now, the idea was to maximize the F1 score to find our optimal threshold beyond which we get maximal number of correct outputs and minimal number of incorrect outputs. But the limitation was that this thresholding method was not generalizable across models, and within a model, it wasn't generalizable across tasks. For example, this is a plot between the original MMLU dataset and the shuffled one, and you can see that there is a difference in distribution which affects the optimal thresholding value as well. We can also see that the optimal thresholding value changes across models, but not just across models. Within the same model, it changes across data sets, and within a data set, it changes across original and shuffled versions of it. Therefore, identifying that finding a global thresholding value is quite cumbersome and would require exhaustive testing. We can also see if we do detect a global thresholding value and we keep it constant across models or even within a model across data sets, the performance changes drastically. Now, our second method was to just ask the LLM to give a confidence score on its output and compare it with the actual log probability values and the correctness of these answers. However, this was a very weak methodology as these models displayed very high overconfidence behavior. And only 2% of the time, GPT detected its false outputs in MMLU dataset. As at the end of the day, these models are token generation models. So you can't really expect them to understand their own intrinsic values to flag hallucinations. Moving on, our final proposed technique was to use the top K token probability distributions to understand patterns to help us identify hallucinations. Now, the assumption here was that for correct answers, the LLM would have a much higher probability for the correct token, with lower probabilities for other options, indicating confidence in its answer and its correctness, which would create a bigger spread and a bigger difference between probabilities in that distribution. Whereas in incorrect responses, the LLM may be confused between the various tokens available, and the top K token probabilities would be much closer and similar to each other, leading to an incorrect answer, as the LLM is not sure about what the correct answer may be. Now, given these assumption of the patterns, we used this technique and tested it, and we used metrics like KL divergence and mean log-log difference to measure probability concentration. And we compared this distribution across correct and incorrect responses across our models. Now, for KL divergence, we saw that it was much higher for correct answers and much lower for wrong ones. And this follows our assumption because it indicates a bigger spread in log probabilities when we're looking at a correct answer because of a higher confidence in one rather than compared to very lower confidences in the other options. Whereas the KL divergence being low for wrong answer also follows our assumption because it shows that the log probabilities are much closer to each other without any distinct token in them showing higher confidence. Now, the same results are for our log prob difference. It is much lower for wrong answers because the probability values are much closer together, whereas it is much higher for correct answer where there's a bigger distribution and bigger spread of probability values across tokens. Now, the conclusion is token distribution analysis provides a relatively robust signal for hallucination detection, and by far in our proposed methods, this method particularly stands out as interesting. Now, if you look at some of the data more in detail, we see that the looking at values for each model and the data sets being used, the KL value is pretty similar in each model across different data sets, shuffled and unshuffled. For example, if you look at GPT 3.5, the KL incorrect and correct remains close word together across the MMLU Med MCQ and Science MCQ dataset between original and shuffled. And these results persist for Llama and Gamma as well. However, for the log prob distribution, we see a lot more variation, which indicates that it might not be the best identifier to catch hallucinations and identifying these patterns in distribution, which would require further study. However, KL divergence still stands out as a good indicator to catching hallucinations. Given the low variation across datasets and its consistent performance across models, this indicates as a fruitful path to follow and further analyze as a potential means to detect hallucination in LLMs. Now, at the end of this, we wanted to compare these different methods that we use to detect hallucinations. So for the log probability thresholding process, the strength was it is a very simple and easy to implement method. However, we saw the variation in the optimal thresholding values and the variation in performance while setting a standard thresholding values. So there's a high inconsistent results across models and data. Now for the self-assessment test, although it requires no external analysis or fine tuning, there is very high overconfident rates in these models to assess their outputs. The most promising method was the top K analysis method, where we studied distributions of the top K token probabilities. This was both robust and captured nuanced patterns, which were able to detect hallucinations across models, but also within the same model across datasets. The only limitation is it adds additional computation to generate these top K tokens rather than just one. Now, to conclude our study, to recap, initially we just wanted to show proof of concept of certain methods that can be used to detect hallucinations in simple vanilla models without adding any fine tuning or adding additional components to the model. Now, we tested these in our three methods across data sets, found limitations and strengths of some methods. But at the end of the day, we demonstrated that token probability distribution patterns are effective indicators of hallucinations and are the best method of identifying. Now, we know a robust hallucination detection framework is essential with the growing reliance on these models for enhancing trust and transparency in LLM interactions. And Top K token analysis offers a promising path. Just to finish this presentation, we want to talk about a bit about our limitations. First of all, we only focused on MCQ data, and we know most of these tasks are on general tasks leading to comprehensive answers. Now, we need to test these methods on those scenarios as well. Other than that, we kind of need to improve computational efficiency of these methods, but also extend these testing on more state of the art models like GPT 4.0, Gemini, or Claude, which we weren't able to do so because of cost restrictions. Finally, just to add, Some of these models don't provide log probability values to their user, which might seem like a limitation to our proposed methods. Our purpose was to show proof of concept of the functionality of one or two of these methodologies to create to pave a pathway to further exploration on this particular technique. Now, by proving this proof of concept, we would budge companies and models to integrate these methods within their LLMs to flag hallucinations and improve interactions with these LLMs. I hope you enjoyed our research and our presentation, and thank you for your time and attention.